Okay, let's get started. If the tendency for the discussion keeps going down, I don't know whether I need to prepare the next discussion. Okay, this week we are going to talk about neighborhood iterator. Recall last time we talked about image region iterator. It provides you a sequential and efficient access to image content. Okay, about how efficient. I wrote a code to access image content with and without iterators. And this table lists the running time for both cases. No matter read or write operations, direct access, you can see the running time is much larger than the one using image iterators. And this week, yeah.
Sorry, question. Are these slides available on my site?
Yeah.
Okay.
Just that table. I mean, I made that one slide.
Table,
yeah, and the homework one, I uploaded the homework one slide to the smart site. And this week we are going to learn about a little bit another iterator, which is a little bit more complicated but more commonly used. Okay, first we will understand what a neighborhood is in ITK and how to use an ITK neighborhood iterator to access pixels in neighborhood. And then we will use the neighborhood iterator to implement a convolution filter. Okay. As you have learned about using Gaussian filter to do smoothing, so you may be familiar with the concept of neighbors of pixels. Generally speaking, the neighbors of pixels are the pixels which are spatially adjacent to a given pixel. In 2D case, you can think of four connected region as the neighbor of a pixel. That's the horizontally and vertically adjacent 4 pixels, or the 8 connected regions, which contains that 4 connected region and the 4 diagonally adjacent pixels. ITK extends the neighborhood concept a bit further. In ITK, a neighborhood is a set of pixels which are at fixed positions relative to a reference pixel. We call this reference pixel center because for the common regular rectangular neighborhood, that reference pixel sits in the middle. And the section 11.4 of the ITK software guide introduced the neighborhood iterators. It briefly introduced some basic concepts about neighborhood, and then its 2 subsections describes neighborhood iterator and shaped neighborhood iterator. And for most of the image processing applications, neighborhood does not need to be as complex as arbitrary shaped. For most of the applications, it's just the common, very common rectangular ones. And its size is defined by a radius. And the shaped neighborhood is defined by user. You can just specify a list of offsets of the pixels in the neighborhood from the center. For example, for the convolution operation, you will just use a rectangular neighborhood. And the ITK neighborhood iterator provides you efficient way to access pixels in a neighborhood. How to access neighbor pixels? First, you have to know the index, the position of the reference pixel, and then know the offset of the neighbor pixel from that reference pixel, and calculate the index from of the neighbor pixel, and then access the pixel. And neighborhood iterator, they can calculate this for you, so you do not need to calculate the index of the pixel by yourself. You just tell the iterator what the offset is. Okay. Like I said before, you need to specify the size of the neighborhood. In ITK, for the rectangular neighborhood, it's defined by a parameter called radius. Radius is a one-dimensional vector. I mean, each component of the radius stores the extent of the neighborhood in pixels along the corresponding dimension. So the side length along a particular dimension is the corresponding radius component times 2 plus 1. That 1 is for the center pixel. So the side length of a neighborhood is always odd. And here is an example of 2D neighborhood of radius 2 by 1. So there are 2 more columns on the left and right of the center pixel, and 1 more row on the top and bottom of the center pixel. And one way to dereference pixels in neighborhood is to think of the neighborhood as a one-dimensional array where every pixel has a unique integer index. We call this index neighborhood position. It is determined by increment from the upper left forward corner of the neighborhood along the fastest increasing dimension. First is column in x direction, and then a row in y direction, and then slice in z direction if there is a z direction, and so on. And the neighborhood iterator also provides you a more intuitive way to access pixels in neighborhood. That's just by the offset. For example, the pixel at position 0, its offset from the center is -2, -1. And for example, this point, the offset is 1, 0. And the other important parameter about neighborhood is stride, which is the difference of the neighborhood positions along a particular dimension. For example, in this case, the stride in x direction is 1, because the difference between the position of these 2 adjacent pixels is 1, and the stride in y direction is 5. Yeah. So if you think of this neighborhood as a 2 by 1 by 0 neighborhood in 3D, then what's the stride in z direction? 15? Yeah, yeah. So you can easily convert the stride to the size and vice versa. Okay, so like I said, the neighborhood positions are very important because you have to use that to access the pixels in neighborhood. How to create a neighborhood iterator? You have to specify the radius of the neighborhood and the image on which you are going to perform operation on, and the region of the interest of the image. And the syntax of the neighborhood iterator is almost the same as that of the image region iterator, such as increment operation and check whether the iterator points to the end position of the region. Okay, this is a example neighborhood. I mean, the numbers in the boxes are the pixel values. So now if we have a neighborhood iterator points to this neighborhood, how can we access the pixels? We can use the getPixel function to read the values at a particular neighborhood position. For example, position 7. That's the position for the center pixel. Then it will return you 0.7. And you can also call this getCenterPixel to get the pixel value of the center pixel. Okay, then how to get the length of iterator and the stride length. The size function returns you the number of pixels in the neighborhood. So in the 2x1 neighborhood, the size is 15. And there is another member function of neighborhood iterator. It's called getSize. That size will return you the size, n-dimensional size of the neighborhood. So for that 2x1 neighborhood, it will return you 5x3. And if you divide that size by 2, you will get the position of the center pixel. So we assign this to C. And if you want to know the stride in y direction, you set the parameter to be 1 to indicate that's the y direction and call the getStride function. Okay, this is the same as before, getPixel at position C. And the other one is what's the pixel at position C minus 1? Because the stride in x direction is 1. So if C is not on the boundary on this line, so C minus 1 will give you the position of the pixel adjacent one pixel away along the negative x directions. Is that clear? Okay. And similarly, if you subtract C by stride in y, it will give you the position of the pixels 1 pixels away in the negative y direction. So this pixel is pixel at position 2. And C minus 1 will give you the left, the upper left pixel of relative to the center pixel. Okay, the increment operation. So in image region iterator, the increment method just moves the pointer of the iterator to the next pixel. And in neighborhood iterator, it moves the center pixel, and therefore the entire neighborhood will shift.
That's why I say wow.
Oh, okay. Okay, so if you have a symmetric, oh, by the way, the neighborhood is symmetric across the center point in every direction. I forgot to mention that. So if you have a symmetric region of interest, which is defined by radius, and you want to move it around the image, so what will this kind of procedure remind you? It's similar to the process of convolution. And to do convolution, you will need three things. One is kernel. That's the weight mask. And you have to have a method to access a region. Oh, to access a part of the image. I mean, that part has the same size as a kernel. And the other way, and you also have to have a calculator to compute the inner product between the kernel and the image region. Okay, first, for the kernel, you can use neighborhood operator. That's a class, that's an ITK class to implement. It's derived from neighborhood. You can think it just as a neighborhood, but every pixel has a value. I mean, you can define it by yourself, or you can use the predefined operator. There are the subclasses of neighborhood operator, such as Sobel operator for age detection, Gaussian operator, and how to access the image. Then we have just talked about that we can use the neighborhood iterator, and you have note that you have to set the radius of the neighborhood iterator to be the same as your kernel. And the last thing is the inner product calculator. The neighborhood inner product, this class will provide you a calculator to calculate the inner product. So it's two parameters or two neighborhood. So because the neighborhood operator is a neighborhood, and also, I mean, the kernel is a neighborhood, and the image region dereferenced by the neighborhood iterator is another neighborhood. So you can just send this two to the inner product calculator. Okay, so these are the process to do a convolution for n-dimensional image. First, design a kernel by yourself or use a predefined one, and then move the neighborhood iterator, let it traverse the image, and then at every position calculate the inner product. Oh, this is a pseudocode for the convolution. First, you define your inner product calculator as IP, and then you define an operator. Here it is a derivative operator. It's a subclass of that neighborhood operator. And you set the order to be 1, and then set the direction to be 0. This will gives you a kernel to calculate the partial derivative with respect to the first dimension, and then create that operator with length only in the specific direction. That's the first direction. And then create an iterator by specifying the radius, the image, and the image region. Okay, then move the operators to the beginning. This is why I said this is pseudocode, because it should be go to begin, not set to begin. And then let the iterator go through the image, and at every position calculate the inner product. Okay. Any question about this? Okay, though in the code there's no explicit reference to the dimensionality, so it is easy to apply to an image of arbitrary dimension. There's a group of filters in ITK, the neighborhood operator image filter. It can do what I showed you before. I mean, perform a convolution, not just convolution, perform a kernel and calculate the inner product at every possible image position. And you only have to set the input image for this filter and set the corner, and it can do the rest. And if you want to do any filtering on the face image as pre-processing for homework 1, and don't know how to start with, you can read chapter 6. Of the software guide.
Question.
Yeah.
When you have a convolution filter, how do you deal with edges?
How do you what?
Not just a convolution filter, the neighborhood iterator. How does that deal with edges? For example,
You mean detect edges?
No, the edge of the image.
Oh.
Yeah, so the region is going along, and it pushes the region outside the image.
how does that work?
Oh, it's a good question. I'm going to talk about that in the next slides.
Oh,
Yeah, thank you to ask that questions. Okay, so how about if the neighborhood moves, outside the image? The out-of-bound pixels have no values. Then how to define the operation? So there is a class called image boundary conditions. The subclasses of it will provide you some rules of how to estimate the out-of-bound pixel values. The first one is very easy, called ConstantBoundaryCondition. It will set the values of all the out-of-bound pixels to be a given value. The default one is 0. So this is not good when you want to detect the edges in the image. So it will produce fake edges on the boundary of the image. And the other one, a more complicated one, is periodic boundary conditions. This one will just repeat the image in the whole space. So if it goes out, I think you will get the idea. Just like the Texton, Dr. Carmichael just said before, you just repeat the image. So every pixel in the space has a value. But this is not good for the medical images because they are not actually periodic. This is there's one called zero flux Newman boundary condition. This is the default value for the boundary conditions for neighborhood iterator. You can tell from the name it's not a very easy boundary conditions. And actually, I don't know. But there's one sentence description in the software guide. You can read that. I mean, I don't understand it a lot. And so it's on page 725, if you're interested. Okay, so for the neighborhood operator image filter, you can use this member function to reset the boundary conditions. Okay, and there's one more thing about the smart neighborhood iterator. If you search this as a keyword in the software guide, it appears only once. I only know that it is used internally by some filter. Yeah, and you can find this on the ITK.Oxygen web page. So that's all I know about it. And one more thing is about numeric traits. Also, this numeric traits, you can find this on the Oxygen web page. If you want to know more about it, you have to read the source code. It is in the ITK source/code/common directory. Oh, directory, sorry. So it defines some numeric properties for some fundamental data types. For example, the mean value, max value, and whether a value is positive or negative. For example, can you guess what's the maximum value for Boolean type? There are only two options. And well, I can tell you it's true because I guess because true corresponds to 1 and false corresponds to 0. And it's also easy to guess what's the max value for unsigned char. Is the char correspond to 255? Okay. That's all for today's discussion. Do you have any questions? Oh yeah.
So for the homework on part 3, I'm interested in counting edges in the picture. So it was suggested that there's a class, like a statistics class that can count.
We count ages?
To count edges, yeah. So that one. So so I guess my question is, what class counts edges, or what's the ITK?
Count ages?
Yeah.
Oh, you want to use ages to define the interestingness?
Yeah. So.
Like I said, I know that Sobel operator can calculate, can detect age for you. Sobel.
Well, the Sobel operator can.
Yeah.
The canny operator.
Yeah. I mean, it cannot detect, but it can calculate how likely a pixel lies on the edge. You can't calculate, count the ages, because, how do you define a age? It's...
Right, okay.
Yeah. I think...
So what's a good way to use the canny edge detector, or maybe the Sobel edge detector? What's a good way to use them?
Use them...
To calculate regions that are... Or calculate the face images that are interesting. So,
We have to use some kind of the...
Okay.
We're getting feedback. We have to use some mechanism to decide which of the faces are interesting and which ones are not. One of the suggestions was use the canny edge detector. Yes. Where did you read it? I thought it was suggested in the PDF of homework 1. Right, so are one idea would be to that next image to calculate what is interesting.
Just count the pixels. I mean, above a threshold. That's the easiest way to do it.
So, count how many are white to indicate a good edge.
Yeah. For example, above 50, I think it is as an age. Just count that.
Okay. I guess that's one way. Another question.